So pick up from where we left over, which is allylic compound. Again, at the very beginning, let's just think about what is the definition of an allylic compound. So whenever we're talking about an allylic compound, you can either have allylic CH, allylic radical, allylic cation, or allylic anion. But nevertheless, all these allylic compounds have the same general formula, which means you have a double bond that is adjacent to that CH group, or that radical, or that cation, or that anion. All right, so if we look at this molecule here, what are the allylic CH we have in this molecule? All right, so they are CH groups right adjacent to the double bond. So if we think about it, these two CH group are my allylic CH. These two CH group are my allylic CH. All right, so we're looking at, well, CH or radical or cation or anion that's adjacent to a double bond. So in our last lecture, we went over some experimental observations, which basically we talk about the stability of the allylic radical, and we figure that judging by the experimental observation, the bond dissociation energy of these allylic CH is considerably smaller comparing to non-allylic CH group. Or in the other word, what we're saying is allylic CH or allylic radicals are much more stable comparing to other non-allylic stabilized groups. So we end our last lecture by looking at the resonance picture of these allylic pi electrons. So here are the three big classes of reactive intermediate we covered so far in this class. On the left, that's the allylic radical. So if we're doing the arrow pushing to connecting the top structure and the bottom structure, we're using the single-sided arrow that's indicating movement of one electron, and that's connecting these resonance structures. For the carbocation, it's the same idea, right? So the electron moves from the double bond onto that single bond, and we end up with a carbocation on the left. The carbanion is the same idea. Goes this, like this. And the negative charge moves to the other terminal carbon. So radical, that's a free radical, one single unpaired electron. Carbocation, carbon-centered cation, and carbanion, or carbon-centered anion. So these three are three big groups of reactive intermediate organic chemists talk about a lot. And all three of them are super stabilized by the allylic group. Again, when we're saying stabilized by the allylic group, we're just saying, hey, next to that reactive intermediate, we have a double bond adjacent to it. So in the classical picture, we were saying we have resonance structure that can stabilize it. But if we ask this question, just one more layer, why does a resonance structure stabilize these reactive intermediates? Right? Just by saying we have resonance, they are being stabilized, it doesn't answer the question. We're just introducing a new terminology here. So what is the actual physics that's happening behind the stabilization of these resonance destabilization? And what is actually happening if we're looking at the bonding in these allylic compounds from a quantum mechanics picture? So that's what we will be talking about today. And we'll look at that carbanion as an example. It works similarly, and we'll pick it up later on. But we'll use their carbanion as an example just to look at how does the quantum bonding theory actually works when we're trying to use like valence bond theory and the molecular orbital theory to describe chemical bonds in carbanion. So let's look at that. This part should be a quick review. We're talking about molecular skeleton with valence bond theory. Or when we see molecular skeleton, we're talking about, let's just look at the sigma bonds that's happening in the carbanion or the allylic anion. So the structure we have here, let me just draw that again, is something like this. That's an overlay picture of both resonance structures. So what we have is obviously all three carbon here are sp2 hybridized. All right, so in this case, let's look at the center carbon first. The center carbon is sp2 hybridized, 1, 2, 3, 4. So what we have is 4 electrons on the center carbon. And in these 4 electrons, these sp2 atomic orbitals will be used to make sigma bonds. Obviously, we're having a sigma bond between the hydrogen and then the 2 carbon that's adjacent to it. So the 3 hybridized atomic orbitals are used to make sigma bonds. And this singly occupied p atomic orbitals will be used to make pi bonds. All right, so this is a quick review on what we're talking about. And let me just copy paste this structure down because we will be looking at the energy diagram of my terminal carbons. So for the terminal carbon, now we need to make a choice, right? One of them is having an anion on it, or the other way to put it is one of the terminal carbon will have an additional electron. We don't know which one of it, right? One of them is neutral, and one of them is negatively charged. Or the take-home message, when we're assigning electrons into my terminal carbon, one of them is neutral with 4 electrons. One of them is anionic charged with 5 electrons. Again, these sp2 hybridized atomic orbitals make sigma bonds. And my p atomic orbital makes pi bonds. So what is the total picture here? Overall, we have multiple atomic orbitals that are hybridized, that are making sigma bonds with its adjacent atoms. And at the same time, we have 3 p atomic orbitals. And in that 3p atomic orbital, we have a total of 4 pi electrons. All right, so keep that in mind. We'll get back to the p electrons later on and pi bonds later on. With me so far? All right. So now let's do it stepwise. The first step is we look at the sigma bonds. So this one is a quick review. It's like now we know this hybridized atomic orbital is making sigma bonds, and we're sketching the molecular skeleton or sketching how these sigma bonds are oriented. So what that means is what we just derived is every carbon atom is making 3 sigma bonds using its sp2 hybridized atomic orbitals with its adjacent atoms. So for sketching it, so that's the 3 sp2 hybridized atomic orbitals. You have 3 sp2 hybridized atomic orbitals for all carbon atoms. All right, so everything in blue are my sp2 atomic of carbon. On top of it, it's also interacting with the 1s of hydrogen. Or if we were to label these sigma bonds, what we have is between all the carbon-carbon sigma bonds, we have a sigma bond coming from sp2 hybridized atomic orbital. And between my carbon and hydrogen, we have sigma bond that's coming from sp of carbon and 1s of hydrogen. So this is a quick review. We did that before. This is just do it again. Sketch the molecular skeleton of these sigma bonds. All right, so that's the sigma bonds. Now it comes to the fun part that's making the allylic system so special, which is when we're seeing the pi bond, what does the pi electron looks like? So remember, we have 3 p atomic orbitals, and we have a total of 4 pi electrons. Anyway, so before I move on to pi electrons, do we have any questions so far? We're good? All right, so now let's move on to the pi bond. So these p atomic orbitals, we will describe it using a different using a different quantum mechanics bounding theory, which is molecular orbital theory. So remember, molecular orbital theory gives you very good description on how orbitals interact with each other in either bonding and anti-bonding fashion. So in the very simple MO theory we covered, when you have two atomic orbitals come together, you form one bonding, one anti-bonding, right? But in this case, the special thing is we have three atomic orbitals coming in. We're forming three molecular orbitals depending on the shading of your p atomic orbitals. All right, we start from three atomic orbitals. We end up with three pi molecular orbitals. So how are we doing that? So this is the general molecular skeleton we talked about. We have a total of three p atomic orbital from each carbon. So when we're doing the sketching, what we're having is, let's just draw these p atomic orbitals. The lowest energy one would be all bonding. When we are saying all bonding, we're saying there's no node plane, so everything is in phase with each other. So in our lowest bonding molecular orbital, everything is shading all on the top or on the bottom. It doesn't matter how you shade it. And then things get more complicated when we go 1 MO higher in energy. Now, instead of having 0 node, we have 1 node. And that node is dividing my molecule into 2 different parts. So that node will exist right in the middle of the molecule. So that is our node plane. And then we add our atomic orbitals in. And whenever you meet a node plane, you switch the shading of that atomic orbital. And you end up with what we call a non-bonding MO, or something in the middle. Moving on to the highest energy MO, right? The more node you have, the higher the energy is. So we're going from 0 node, 1 node, and then the top one will have 2 nodes. And this is what we have. That's shaded, switch, switch again. So that's how you create or how you sketch the molecular orbital based on their atomic orbital. You first write out the skeleton, and that's what it looks like. And then you put the atomic orbital on there. For the lowest one, we have 0 nodes. And that's the most stable molecular orbital. You go up, you have 1 node, that's the middle one. And when you have 2 nodes, that's the highest energy molecular orbital. So the more nodes you have, the higher that MO will be. As you remember, we were talking about 3 total atomic orbitals, 3 total MOs, and we have 4 pi electrons in them. So when we put those 4 electrons in them, that's how it's organized. All right, so it's here, 1, 2, 3, 4. And looking at it, now we can assign the name of these MO, and in organic chemistry, we use them a lot. So this one, the second one, is called HOMO, or if we write it down, that's the highest occupied molecular orbital. The top one here is called LUMO, and that's our lowest unoccupied molecular orbital. All right, so that's how we create what we call a pi correlation diagram. So this entire diagram here is called a pi correlation diagram for our allylic carbanion. And if we spend a little bit more time just looking at the HOMO of my allylic carbanion, what does that tell us? That tells us now on the bottom you have 1 pi bond that's fully delocalized over the entire molecule. This one is a non-bonding, or it's somewhat telling you this is a lone pair that's also delocalized. But instead of delocalized over all 3 carbon atoms, what it's saying is you have, you're expecting to have electron density on these low, or on your terminal atoms along, not on the middle, because we have a node plane in the middle. And the position of that node plane is determined by the symmetry of your entire molecule. So what that means is, in this case, we can create the same kind of overlay picture from the quantum perspective. It's delocalized, yes, or what that means is, let me just copy that down. If we're looking at the HOMO here, all right, just copy everything down so you're looking at something. So this one is our HOMO. What does that tell us? Is now you have this molecule. You have H2C, CH, CH2. And the position of that negative charge is on your terminal carbon. Or you can imagine each of it to have like about negative 1/2 of your charge. All right, or the take-home message here is, by analyzing our pi correlation diagram, what we're having is, hey, we have a node plane right in the middle of my allylic compound. And because of that node plane, we're expecting the molecular orbital centralized on the terminal carbon. And because my molecular orbitals are centralized on the terminal carbon, that's why my carbanion, my lone pair, is actually delocalized on the terminal carbon. All right? So I'm gonna go back to this our pi correlation picture. How do we feel about it? So what I expect you to know, I don't want you to be, I don't expect you to be able to create this pi correlation diagram just like everything from scratch. No, I don't need you to do that. But if I give you like pi correlation diagram like partially filled, for example, if I give you the skeleton, I don't give you the atomic orbital, can you finish it up? Or like we have a molecule, right? We have these energy levels. Identify the HOMO and LUMO in this pi correlation diagram and try to get information out of it. All right, I'll take some questions. Yes?
For the molecular skeleton, what's the difference between the diagram for the neutral carbon and the center carbon?
It's not, well, so going back to the molecular skeleton, the question is, what's the difference between the center carbon and the terminal carbon? The quick answer here is the center carbon has one sigma sp2, one s sigma bond with the hydrogen, and making 2 sigma bond with its carbon atoms that's adjacent to it. For the terminal carbon, well, it's CH2, so it's making 2 sigma bonds with the hydrogen and just 1 sigma bond with the carbon next to it. Yes? I can't hear you.
On this diagram, is there a positive charge on the
This one is only sketching the atomic, well, the sigma bonds. We're not talking about targets. So this one is only the sigma bond, only contribution of your atomic orbital to make that sigma bond. We'll talk about like delocalization of charges and everything in the pi correlation diagram.
So would you still consider like a singly occupied pi orbital, I guess, as a HOMO? Like if it was just one electron in that, would it still
We'll see that. We'll see that when we're talking about the radical case. All right, we're good with the correlation diagram. You'll also see some of the correlation diagram problems on your Canvas assignment. I didn't put any of these problems in the discussion worksheet, but you'll see some of my expected question in the Canvas assignment next week. All right, so let's move on to extend what our understanding is on the allylic carbanion into free radical and also carbocation, and also answer your question there. So the take-home message here is your allylic carbocation and radicals are likewise delocalized, and that's also likewise being stabilized because of that delocalized pi electron over your entire molecule. So this is a correlation diagram we have created, right? And now it's a good time to think about it. Do you know how to put the electrons into these allylic compounds, into its pi correlation diagram, and identify its HOMO and LUMO? So carbanion, we did it before. So in total, we have 4 pi electrons. And we have 4 because it's like 3 and plus a negative charge, which gives you 4 total electrons. So we end up to have 1, 2, 3, 4. And we went over, this one is our HOMO, and the top one is our LUMO. So HOMO is the highest occupied molecular orbital. LUMO is our lowest unoccupied molecular orbital. Likewise, we can do the same for the free radical. So it's a free radical. So now the entire molecule is neutral. We only have 3 pi electrons. We have 1, 2, 3. So this one, some people call it SOMO, or singly occupied molecular orbital. It is also correct, at least in your textbook, it's also correct to identify it as HOMO. And on the top, we have LUMO as well. All right. And for the carbocation, now we have 1 less electron comparing to the neutral molecule. So what we have is only the bottom 2 go to our pi 1 MO. So my HOMO becomes my lower one, and my LUMO is the middle one. And if you're interested, sometimes people also care about like LUMO plus 1, and this one is HOMO minus 1. But that's just like additional. You don't need to know that. All right. And if we're doing the similar kind of delocalization picture like what we did with our carbanion, so in this case, what we have is H2C, CH, CH2, negative charge delocalized. What we expect is at the terminal CH, on the terminal carbon, each of it will have a negative 1/2 charge. For the radical here, it's the same idea. That radical is in this non-bonding MO. So CH, CH2, delocalized. So what we expect is 1/2 of that free radical on each of the terminal. The cation is the same idea, but now we're talking about a cation, or it wants electron. So we're looking at its LUMO. So what we have is structure like this. So we have plus 1/2 and plus 1/2. All right. So before we move on to look at a practice problem, again, I like to give you a take-home message. So if this is the only thing you remember from this entire class, this is it, all right? So first of all, allylic radicals, cations, and anions, they are more stable. They're more stable because of the delocalized electron or positive charge or negative charge. In classical bonding theory, we also use resonance structure to try to depict that electron delocalization. And the fundamental reason allylic species are stable is because your pi bond is delocalized over all 3 atoms. And the second take-home message is here. Your partial radical, cation, or anion characters are only present at the terminal carbons. All right, and this is all because the second molecular orbital we talk about has a node right in the middle. So whatever character we're talking about, whether it's an anion or a free radical or a carbocation, everything is centralized on your terminal carbon. So if you are to remember anything, these are the take-home message you need to remember. First of all, allylic compound, they're stable. But we're seeing allylic compound, you just have a double bond adjacent to that group. It's stable because of electron delocalization. And these partial radical, cation, or anions, they're always on the terminal carbons. right? Any questions on the allylic before we move on to do problems together? Yeah.
Do you mind just going over again why you decided on the previous, why you decided homo on the bottom one was the.
So this one is homo minus one. So let me just delete those extra. But when we're talking about homo, what does homo mean? Homo is highest occupied molecular orbital. You look at this molecular orbital, you'll find that highest occupied molecular orbital. So naturally, by its name, these two are my HOMO. They're highest occupied molecular orbital. For the carbocation, we only have 2 electrons. So that's why this bottom one is our highest occupied molecular orbital. It's the same idea. LUMO, lowest unoccupied molecular orbital. So one of the questions I might ask you to do is sketch the HOMO of some allylic radical. So you should be able to sketch this molecular orbital for me. All right, so it's not hard. It's just like you write it out, and then it becomes really obvious. HOMO, just highest occupied. LUMO, lowest unoccupied. That's all. And let's do one problem together and see if we have any questions later on. So now we went over all these allylic compounds, and we know they're stable, and we know the radical or the cation and anion are on the terminal of my molecule. So why do we care about it? So here's an example question. Let's just read it together and see how I expect you to use this kind of knowledge in solving chemistry problems. So the question reads, hydrolysis of allylic chloride forms 2 products. So the reaction is given here. This is a allylic chloride. When we say it's allylic chloride, again, the reason is this carbon Cl bond is right adjacent to a double bond. So that's why we call it an allylic chloride. All right, so hydrolysis of allylic chloride forms 2 different products, A and B. So we have A and B and C here. And for some reason, C is not being formed in this process. And given that this reaction proceeds via a carbocation intermediate, so I use my arrow pushing here to show you what the first step is, and you should be able to draw that carbocation intermediate based on the arrow pushing I give you here. Can you explain why product A and B are formed, but product C is never observed? All right? So that's what we have. We have the reactant. We also have a OH minus group around acting as the nucleophile. And among A, B, and C products, we're only forming the top 2. We're never observing the bottom one as our product. Why that is the case? So let's just follow this logic and draw our carbocation intermediate first. What does that look like? We're breaking the chemical bond here. Both electrons go to the Cl. We're forming a carbon-centered cation. In this case, a allylic cation. So this is what we have. Hydrogen, hydrogen, and a plus. And if we look at the product, what we have, A looks sort of obvious, right? You just have a OH minus around, and that OH is attacking my carbocation here. It's just like you have 2 charged molecules, your iron pairs, you're forming our product A, which is quite obvious. Now the question comes, why is B formed and C is not? So if we look at this allylic compound, again, we're talking about allylic compound. We know that that carbocation can be delocalized because this is a allylic compound. You can draw resonance structures of this allylic compound. So for doing that, what we end up having is actually, you can do the arrow pushing or you can not do it. So this is what we have. Hydrogen, hydrogen. And that's the resonance structure you can draw from that allylic carbocation. And that explains the formation of our product B here. All right? But if you look at it, this is the allylic compound we're talking about. In all cases, this is my center carbon of the allylic group. And as we just talked about, my center carbon will not have any carbocation properties, right? So the center carbon does not have any carbocation properties. And we did that analysis before. Again, what we have is that C LUMO of my allylic carbocation, and because we have a node plan, your center atom just doesn't have any positive charge. Or the other way to put it is you can never draw a resonance structure with a carbocation on the center atom. And that is why your product C is never being formed. So here's a very good opportunity I want to pause here, as organic reactions can be complicated, and try not to remember what is happening. You will use that in 14D a lot. Just know what the reaction mechanism is, what the reactive intermediate is. And by understanding the property of that reactive intermediate, you don't have to remember what the product is. You can derive it out. All right, so that's why I want to spend some time on this example. It looks like we're predicting selectivity of a chemical reaction, but we're doing it by understanding the property of my allylic intermediate. All right, any questions on the allylic compound? Yes?
Why do we use the LUMO for the carbocation, but we use the HOMO for the...
So if you think about the nature, so the question here is why do we use the LUMO for carbocation and we use HOMO for the carbanion? So when we're having these kind of reactive intermediate involved in a reaction, a carbanion with a negative charge with an extra lone pair is more likely to act as a nucleophile. It's donating its electron to some other group. So that's why we care about a molecular orbital with electrons, which is like HOMO. Right? Alternatively, when we have carbocation, it has a like cation, right? It's missing electrons. It wants to accept electrons. It's acting as an electrophile. So we want to talk about where we can put that electron in. So that's why we're using the lowest unoccupied molecular orbital, or LUMO, to describe the chemical property of a carbocation. Yes.
So we put the positive on that carbon in the second one, but there's two hydrogens attached, so how is that positive charge there?
Which one?
Yeah, this one.
Oh yeah, that one has only one hydrogen. Sorry, that's a typo. That's my bad, yeah.
Does the central one have hydrogen?
Yeah, central one also have one hydrogen. It's always have one hydrogen in both cases. All right? Yes?
The top carbon for sulfate, what is the electron for the double bond?
So this green arrow is just showing the electron pushing between these two resonance structures.
Oh,
Yeah. So whenever I'm doing arrow pushing in two different color, it's two different sets of arrow pushing. Like, don't read it together. All right, so allylic compound, again, the take-home message here, it gives you stabilized radical cation and anion. These are very important reactive intermediate you will encounter in all kinds of organic reactions. So that's the allylic compound. Now we have about 15 minutes. Let's move on to look at another class of very important pi complexes. So these are called conjugated dienes. So what we'll do, we'll first start looking at the nomenclature of conjugated dienes. So what is a conjugated diene, right? How to identify that conjugated diene in any organic molecule. And then we'll do the same. We'll write out the pi correlation MO of the conjugated diene and try to understand the chemical bonding in the conjugated diene. And at the end, we'll see some of the properties that's coming from that special bonding pattern of the conjugated diene. And hopefully we'll have enough time to do an example question together. So first thing first, nomenclature. So when we say an organic compound is a diene, what it means is that compound has two double bonds. And that's it, right? Any compound with 2 double bonds are called dienes. We have 3 big classes of dienes you can work on. The first one is called a non-conjugated diene. So anything that's not conjugated, that's a non-conjugated diene. What it means, you have double bonds that's separated by saturated carbons or sp3 carbons. Right, so if we look at this 1,4 pentadiene as an example, so 1,4 tells you the position of the double bond, penta tells you we have 5 total carbon, diene tells you we have 2 total double bonds. I'm not going to test you on nomenclature, but it's nice to get familiar with what's the logic behind these names. And if we look at it, this center carbon here is sp3 hybridized. So whenever you have double bonds that's being separated by saturated carbons, 1 or more, these are called non-conjugated dienes. So that's the first big class. We can also have a second class where you have the pi bonds sharing one single sp carbon. All right, so that's a single sp carbon that's being shared between 2 different double bonds. These are called allenes. So 1,2 propadiene or allene. And if you think about the pi bond in this compound, what it has, these pi bonds will be perpendicular to each other. So these pi bonds are perpendicular to each other, so they're not overlapping with each other. That's why they're not conjugated, or they're not delocalized over the entire molecule. And our leading character here is our conjugated diene. So whenever we have a conjugated diene, so 1,3-butadiene is a most straightforward example here. What we have is just alternating single and double bond, and all carbon atoms are sp2 hybridized. All right. So again, this is just a quick reminder in why do we care about hybridization and why do you need to know how to quickly assign hybridization into carbon atoms. So 3 different types of diene. If they're separated by sp3 carbon, they're non-conjugated diene. If they're separated by a sp carbon, they're called allenes. And what we care about are conjugated dienes, where all carbon atoms are sp2 hybridized, and they're basically alternating single and double bonds. All right, so that's the nomenclature part. Moving on to look at the pi correlation molecular orbital of my 1,3-butadiene. So here, again, what we have is a conjugated diene, and the characteristic here is alternating single double bonds, or sigma pi bond if you like. Actually, let me do single double bonds because and in here, like what we just said, all carbon atoms are sp2 hybridized. So if we look at the electron diagram of all my carbon atoms, what we have is all carbon atoms are sp2 hybridized. They're all singularly occupied. They're neutral, 4 electrons. So in this case, the same idea, right? All my sp2 hybridized atomic orbitals forms sigma bonds. So for each carbon, it's making 3 single bonds with its adjacent carbons or hydrogens. And then my p atomic orbitals will be used to create our pi correlation diagram. All right, and now we know we have 4 p atomic orbitals. So how many pi molecular orbitals we'll end up having? We start from 4, we end up with how many MOs? We don't destroy or create MOs out of nowhere. So we start from 4 atomic orbitals. We end up with 4 molecular orbitals. All right, you start from 4, you end up with 4. And the way to draw it is here is a skeleton. I didn't show any of the hydrogen because hydrogens are not involved in making these pi correlation diagrams. And now let's just think about it. We have 4 total molecular orbitals. How do we draw it? And here is the logic. The lowest energy one will have 0 nodes. The one up will have 1 node, and then 2 nodes and 3 nodes. All right, so the larger number of the node we have, the higher energy we have. So the best way to put it is let's just draw the position of the node first. So 1 node, that's going to be in the middle. 2 nodes, that's going to be between here and here. And 3 nodes is in between all the carbon atoms. All right, so 0, 1, 2, 3. And now we can write our p atomic orbitals and shade it based on the position of the node plane. So in the bottom one, we have all shaded. There is no node, so we don't have to change the shading in any way. And then here, these 2 have the same shading. And between C3 and C4, we're flipping the shading because we meet a node plane. Whenever you meet the node plane, you switch the shading. And here, it's switch, didn't switch, and switch on C4. And at the very end, we're switching at every node plane. All right, so with me so far, look at it. You identify how many MOs we have. You put your number of node plane in these MOs, and then you create the sketching of your molecular orbital. And now we're ready to put electrons into my pi correlation diagram. How many pi electrons we have? We have a total of 4 singly occupied p atomic orbitals. So naturally, we have 4 electrons. So if we put the electrons in, that's 1, 2, 3, 4. The last step, labeling HOMO and LUMO. So HOMO, in this case, which one is my HOMO? Pi 2, right? So that's the highest occupied molecular orbital. Pi 3 is my LUMO, which is my lowest unoccupied molecular orbital. Okay? All right, I think I have time to finish talking about insights of these conjugated dienes. So just look at it. In our lowest energy, pi 1 molecular orbital, so I'm just going to highlight this for you. All electrons are fully delocalized. All right, so that's telling you for every chemical bond, C1, C2, C2, C3, C3, C4, they all have some flavor of the pi bond because the pi electron is fully delocalized in my lowest energy occupied pi MO. So that's the first piece of information. Second piece of information, so if we look at the HOMO, we have a node plane in between C2 and C3. So what the HOMO tells us is C1, C2, and C3, C4 will have more pi character, where C2 and C3 have less. So the consequence of these 2 molecular orbitals is the following. So that's the 1,3 butadiene that people can get. By actually doing quantum mechanics calculation, you can measure, well, we'll tell you what the bond length is, right? So between C1 and C2, it's a double bond. It's like 1.33. It's like a double bond in the ethane. between C3 and C4, it's the same idea. It's a double bond. It's pretty good double bond as comparing to the normal ethane. But if we're looking at the chemical bond between my C2 and C3 here, in comparison with a pure single bond in just butane, we can see this single bond is considerably shorter comparing to a normal single bond that's not in a conjugated diene. All right, so this bond is 1.46, and in the bottom, without any conjugated diene, a normal single bond is 1.52. So now my question is, why is this single bond in my conjugated diene is shorter than your normal sigma bond? All right, so let me just keep this question. We'll go back to our pi correlation diagram and ask you to think about it. Right, so the single bond between C2 and C3 is shorter than your normal single bond because it still has some pi character. All right, that's coming from our lowest energy MO here. In my lowest energy MO, all electrons are delocalized over all 4 carbon. So even if it looks like in my HOMO, this is a single bond, that's a node plan, but in my lowest energy MO, it still has a little bit of the pi character, making my C2, C3 a stronger bond comparing to your normal single bond. In our next lecture, we'll start to use some of the knowledge we learned today, try to rationalize a little bit more about the property of the conjugated diene, and also see some problems we will do together. I hope today is not too much orbitals. Again, it's just about what is a molecule, right? Why do we care about these reactive species? All right.